We're on the very last session now, where we're going to go through both the developer installation procedure as well as some high-level suggestions about developing RMG, maybe a little bit of my own absent-minded ranting about future directions, and of course, Q&A as we go, because I think this, for those of you who are new to developing, and Python especially, will probably be the least familiar, because we're not really going to talk about much chemistry at all for the next little bit here, which maybe that's a relief to some of you, who knows. But anyway, I'll go ahead and get us started here. Yeah, maybe. How do you zoom on Firefox? Oh, that's going. Okay. Yeah, so earlier, I said that rmg.mit.edu is the home base for all things RMG. That was only partially a lie. The other home base for people that actively develop RMG is github.com/reaction mechanism generator, which I will send into the chat so that you can navigate here as well. But this website is what's called a repository on GitHub. So GitHub is what's called a version control software. It allows you to have one central copy of code which other people can download, modify, and then upload their changes to. And it's done in an intelligent way so that if Richard makes some changes, I can leave comments on them. I can pull them onto my machine and try them out. I can make more changes on top of his. Somebody else can try them, and then we can all combine them at the end. So obviously, for a really distributed project like RMG, where we have lots of people working on it, that's really helpful. So if you'd like to be a contributor, this will be the way that it goes. So it's worth learning. Some of the repositories which you'll find within our overall organization, of course, there's RMG Pi. So in general, whenever we refer to RMG, what we actually mean is the code that's in this repository. This is the actual driver code that's responsible for thermochemistry estimations and reaction generation, as well as some of our more basic simulators. And then the other thing that you'll see here, which I'll point out, is reaction mechanism simulator.jl. This is our Julia-based sort of alternative to like Cantera, Chemkin, and the really basic simulators that are prepackaged with RMG. The latter are prepackaged with RMG. So RMS has lots of really fantastic functionality for sensitivity, and it has more diverse types of reactors than RMG has by default. So the Docker image that you downloaded earlier includes RMS. And then as a developer, you can make a choice whether or not to include it. But I invite you all to poke around on the GitHub. Sorry, was there a question?
Docker image is equal to
yes, the question was if the Docker image includes Cantera, and it does. Yeah. 2.6. Yeah. Yeah, so I invite everyone to poke around on all the repositories that we have here. RMG's greatest strength is that it's open source. So you can go back and see when I was making really snotty comments before I learned how to be nice on all the pull requests. And you can see some of our other in-progress work too. So ARC, AutoTST, and T3 are three really cool tools built on top of RMG that extend it in really fantastic ways. They're worth looking at and reading the corresponding publications for. I won't talk about those right now. We're going to focus on RMG and specifically the developer installation process. So what we went through this morning, and I've got these windows side by side because this is how I suggest trying to get things installed. What we went through this morning was the regular suggested user install. Are you messing with this, Jonathan? We went through the regular Docker-based installation. If you scroll down on this page just a little bit, you get to developer installation from source. And you'll follow 3.2.1 which gives you detailed instructions. And again, the Docker image has already done all why we use Docker in the first place. Detailed instructions for getting everything up and running. So I'm not going to go through these step by step because the whole installation process takes a little while, and I'd rather show you the results and then talk more about development. But I do have it completed on the right, so you can see at least what it looks like on the end. So step one is downloading what we call a package manager. The one that we choose is Conda. There are other ones. So if you prefer something else, something feels more natural to you, absolutely go for it. Conda will work the best with RMG. We specify everywhere you can find it on Conda, so we highly suggest it. We particularly suggest using the MiniForge variant of the Conda installer, the link to which is here. Follow these installation instructions at that linked page to download the installer and then run it, and then follow the instructions that the installer tells you. What you'll end up with at the end is a terminal where you can run conda activate base, and then all the way on the left, you should have this indicating that conda is successfully installed and you're just sitting in some empty environment, basically. And I'll add too, I know there was some discussion earlier about the security considerations with Miniconda, as well as the licensing problems with Anaconda specifically. This variant that we suggest, MiniForge, avoids using any of the packages which are not free to use. So rewording that without the double negative, MiniForge is free to use for everyone. So you can avoid any of those challenges. Step 2 only applies if you previously installed Conda, so we don't need to worry about it. Step 3 has you install a few extra dependencies that are required to work. So you can just find your corresponding operating system, probably Ubuntu, or otherwise if you're on Mac OS, follow the instructions here to download Xcode command line tools. What I have here on the right is functionally Ubuntu Windows subsystem for Linux, but again, you get the same result. You just copy that command in and then run it, and you'll end up with those packages. Some of you might already have them installed if you've been developing other tools. And from there, we're actually going to start downloading the code. So the commands here clone from GitHub, from those repositories that I was showing you earlier, the source code for RMG Pi and RMG database. So I've already done that, so I'll just show you here that they are downloaded. So I have RMG Pi and RMG database. Again, we use Git so that everyone can collaborate with one another. Sevi can make a pull request and I can make edits on top of it, or we have branches that are exploring the addition of electrochemistry, so you can check those out and try them locally. The installation process from here, you're going to navigate into the RMG Pi directory. So change directory RMG Pi. If you look around in here, you'll notice that it is the same as the Docker container. So when you launch Docker, you actually are sitting in this same folder, just another copy of it. And then the next step will be conda environment, which is going to create an isolated version of, or excuse me, an isolated environment where we can install all of the external packages that RMG requires. And then you'll just specify the environment file, which has a complete list of those packages. That's going to run a big giant install and then put a ton of different packages on your computer. So these cover a huge variety of different functions. So we have, of course, Python in here. And then, excuse me, I'm actually in the wrong environment. Yeah, so what you'll be left with is an environment called RMG environment. And then within there, you'll have a bunch of packages related to all the different functionality that RMG has. So Python will be there. You'll have things like NumPy and SciPy, which we use for numerical computations. a couple external Fortran-based solvers that we maintain, and then all of the miscellaneous nice little things for like rendering the HTML files that RMG exports at the end, doing machine learning with scikit-learn, RDKit, the universal chemical format machinery for basically all of Python chemistry. So once that's done, you need to just activate that environment. So actually that command that I just did to get back into where I have all of these dependencies installed, conda activate RMG environment, and then you're just going to run the command simply make. So make is yet another external piece of software. There's a file located in RMG called a make file, which is an excellent name. And all that it has is a set of instructions basically for installing RMG Pi. So this is another way for us to make the installation slightly easier for you. We've already put together a set of directions. This is what actually ends up getting executed when you call make in order to get RMG built. That will spit out a whole bunch of diagnostic information as it's running and a lot of warnings. You can ignore them unless the build fails, which it rarely does. But if it does, please raise an error, an issue on GitHub, which I'll show you how to do afterwards, and we can figure it out. So from there, the remaining two installation-related steps are technically optional, but are important for some cases. Sevi mentioned earlier today that setting your path environment variable can allow you to launch rmg.py from any folder. So what we've had to do so far whenever we wanted to run an input file was make sure that if rmg.py is what we're trying to execute, that it has to be in the same location as where we currently are. So if I had an input file in a different folder, I couldn't go to that folder and run python rmg.py. If you choose to make this modification to your path variable, that will work. It's up to you. If that would make your life easier, go for it. And then next is the installation of RMS. So we provide this script, install rms.shell, which you can run as shown here. And it will walk you through the installation process for getting RMS installed. You'll end up executing that script probably like 3 times because it will first check for Julia. If Julia is missing, it tells you how to install it. It then checks for the correct version, tells you how to set the correct version, so on and so forth. But it provides text-based instructions continuously until RMS is eventually installed. A bit of historical context. Previously, as I maybe alluded to this morning, RMS was mandatory in order to run RMG. RMG wouldn't run if you didn't have RMS installed. These days, we've made some modifications to make RMS optional. So, of course, that comes with some costs. RMS has all those fantastic reactors that I was talking about and like sensitivity analysis features. You cannot use those if you don't have RMS installed. And then there's one smaller detail where one of the methods for solving the master equation within Arcane will be unavailable without RMS. Yeah, and sorry, Richard has a...
Very recently, it defers the slow, painful loading of Julia's stuff until absolutely necessary. So there's no cost to having RMS there. It used to be that even having RMS or Julia was a pain in the butt because it was slow every time you even tried to launch load RMG or draw a molecule or whatever, it would do it all. That's no longer a problem. So in fact there's very few reasons to not install it now. You may as well just install it.
If you do get very advanced into development, it can be more convenient to have 2 parallel environments, one with Julia and one without. Running the tests in parallel is much easier if Julia is not installed. But again, like if you're getting to that level of RMG, please reach out. We'd love to compare notes on how to make our lives easier. Yes, from there, it's just the typical RMG usage. So you're up and running and you should be good to go. what I'll spend the last few minutes on here is talking about what you can actually do on GitHub, things to look out for, how to ask for help, and how to get help for yourself as well. So let me switch back to the repository here. Oh yeah, there it goes. Sorry. And what I wanted to show too, in this case, I'm just running the super minimal example. You can see the startup was a little bit faster. So yeah, up to you. Back to the GitHub. So rmg.py, which is already open here. This is your home base for most RMG related considerations. The only other repository that you'll need to worry about are Reaction Mechanism Simulator, which I showed you before, and then RMG Database. So just to reiterate from the talks we've seen today, RMG Database holds our libraries and our families, all of the static data that RMG builds on top of. And then RMG Pi holds the driver code, which is responsible for actually leveraging that data to do interesting science. So first and foremost, if you have a problem installing RMG or you get an error that you don't understand, or your mechanism looks totally wonky, you can come here and you can open what's called an issue. So you'll click this new issue button in the top right. And then what that will allow you to do is fill out a template if it wants to load. There we go. Yes, so if you've identified a bug, you can label it as such. If you have a request for something you'd like to do, if you have a question just about the general usage of RMG, so let's say I found a bug. Again, it gives you more ideas of what to fill in here. As you're filling out issues, please provide as much detail as you possibly can. Please don't leave things out, assuming that we won't need to see them. If you already have it, just go ahead and post it on the issue. It's easier for us to scroll past it and ignore it than it is to ask for it, especially when we're dealing with different time zones. And if you post it at night, I probably won't reply until the next morning. And then all of a sudden, it's 12 hours to wait for a little bit more information. So post whatever you have, fill this out to the best of your ability, and we can get you help. Another worthwhile thing to do is search through existing issues if you have a problem already. So what's not shown in this default view is that there are 43 open issues right now, but there are over 1,200, which have already been closed in the past. Now, not all of those are going to be the exact solution to your relevant problem. But in this example, we had someone with an issue not being able to run a Jupyter notebook within the Docker container, and we were able to get that resolved. So if you were to have searched for Jupyter notebook doesn't open in Docker, that probably would have popped up. You can read through and figure out what else is wrong. Again, another example here where there was a Conda environment step during the developer installation, which wasn't working on a specific type of MacBook. And we were able to get that resolved following the commentary in that issue. And I'll brief sidebar to mention that we are aware that there are lots of challenges with getting RMG to work on ARM Macs, so the Macs with the new ones where Apple built the CPU. Fingers crossed, it's easier today than it was like 2 weeks ago. But again, please open issues as you encounter them with that specifically, because we're pretty limited in our capacity to test that. Almost all of our developers are using Linux and Intel or AMD CPUs, so we can't find those issues as easily. What I'll go through next is the process of introducing changes to the code and then what we call our continuous integration. I don't know why I said it that way, that's just the name. So this pull requests tab, pull requests is GitHub's terminology for saying, I would like to submit changes to the code base. Anything that you put in here will be reflected in the central copy of the code that everyone else uses. If you are able to fix a really pesky bug, we'd really appreciate it if you make a pull request and post the code so that we can help other people with that same issue. And you can sort of look back at any of the almost 1,500 closed pull requests which have been merged in, so that you can see the sort of procedure for figuring things out. So I'll go through this one from a postdoc from our group where she proposed making a pretty small change to a file where it looked like this energy correction was not being applied correctly. So the nice thing about GitHub, again, this is why we use it, it shows you the lines that were changed, and then it shows you the lines where there were additions made. So you can see in this case, there was this energy correction that didn't make a lot of sense, so she took it out. Post this up on GitHub for everyone to see. Critically, now everyone can see on it. So she provided her justification here. You can see filling out this template. And then Matt and Richard were both able to pop on and leave lots of helpful scientific discussion about whether or not it's appropriate to have this correction here. So I think the ultimate conclusion was that we're going to leave it, but
It's something that needs fixing, but that was the wrong solution.
See?
She was absolutely
Yeah.
right to open it as
a thing. So it was like, oh wait, actually, yeah, you're right. There's a problem, but
So this
it's a
is
different fix.
the value of collaboration. We're very happy to have that. So whenever you make pull requests like that, people will leave helpful comments about ways to improve it and directions to go. And then while that's going, there's lots of bots that we have that are going to torture your pull requests with thousands and thousands of tests. So if you scroll all the way down to the bottom of any pull request, there will be this giant brick of status checks. So there are slightly more now, actually. This is a slightly old pull request. But what this does is takes the code that you have modified and then follows the developer installation process and runs our unit test suite. So unit tests cover all the various functionality of RMG. We have just shy of 2,000 of them to cover all of the little miscellaneous edge cases for the, for the for all the different functionality that RMG has. And we run it on different platforms to make sure that it works to the best of our ability on all the different types that we want to support. And then GitHub itself, we have a bot running, which will leave this comment whenever the unit tests are successful. So ignore this. This is fixed in the current version. This is just a little bug from earlier, but we also run on top of the unit tests a set of regression tests. So the regression tests take RMG from yesterday, literally yesterday. It runs a set of mechanism generations to arrive at a fixed mechanism. And then it takes your suggested changes, generates the same mechanisms, or at least executes the same input files to generate mechanisms, and then compares the two. The idea being that we don't want to introduce regressions that cause changes in the generated mechanisms from day to day. Improvements are good, so that's why we have these detailed regression test results, which demonstrate where we might see differences in between your version and the version that we had originally. So you can see in this case, we have a regression test covering aromatics, and the changes introduced in this pull request caused, let's see, one number to change. So the entropy estimated at 300 Kelvin went from 82.78 to 84.16. So sometimes the regression testing apparatus is not perfect, so you'll get erroneous reports of errors like this one actually. So the kinetics are, nope, actually that one was right. Yeah, I don't have an exact example on hand, but occasionally the regression testing apparatus will report false negatives. It will say that there were issues when there weren't. And it's not perfectly reproducible. We are working on improving the estimators for particularly fused cyclic systems, which are known to have non-deterministic thermochemistry estimates due to a more advanced, like it's a graph theory problem. It's an open problem in the world of math, and we poor engineers are just sitting here staring at it. But yeah, so anytime you make a pull request, you'll get to see this, and the developers can help you interpret the results, um, as well as yourself too. It's interesting to see, changing how a thermochemistry estimate works, for example, could modify the overall behavior of the system. So in the last couple minutes here, I just want to highlight some big directions that RMG is going that haven't been published, but that might be of interest. First and foremost, what Jonathan was alluding to at the end of his talk, we're working on slowly making RMG database a little bit easier to get into. So RMG database as it stands today, if you actually go into it, it's giant bricks of Python files. So if we look at, for example, the Thermo database and we go into libraries, these are very nice collections of thermochemical data assembled from actual studies. So really useful to have this kind of information. Unfortunately, it's just really, really hard to interact with. It requires having the full complete version of RMG installed and working in order to query anything in this database. So one big step that we're taking is moving the data from this Python file format into a true database format. So you'll be able to do this in the future, where you can just open with pandas, which is a common, very easy to use Python package for loading databases and interacting with them. And you can get into, in this case, I want to say it's the StatMech libraries to make the data easier to reuse, particularly for training machine learning models, which is something that we're interested in, but of course useful for other things too. Besides that, I think the other big directions you can sort of see for yourself in the list of open pull requests on RMG. So you can see there and also in the issues what people are talking about a lot in terms of what they're hoping to add. Of course, MIT's Wi-Fi is giving up on me a little bit here, but yeah. So you can see Bon, a member of the Green Group, is working with Nathan on adding ML-based solvation corrections. Alone, I want to say, is extending the capacity of our quantum chemical parser to work on other methods. Some of the longer term ones are like upgrading to the latest version of Cantera, which I got partway through. And then I think overall directions that RMG is going, and these will be the subject of talks in the next couple of days, as well as I think there's probably a lot of time for questions tomorrow, especially for things like this. RMG has gradually been moving more and more towards surfaces. So there's a lot of support for surface mechanisms now. We saw the surface representation discussion with Richard this morning. And electrochemistry has been the other big point of focus, particularly lithium. Matt and Sue and Richard have been working on that, gradually getting that up to speed as well. So there's a branch on RMS, which I think adds all the remainder of the capabilities needed there. RMG has some basic functionality in that direction right now. But yeah, with that said, I'll leave the last couple minutes for questions, but also say thank you to everyone on behalf of the whole RMG development team for showing up today and being at the workshop. Our next day is Friday, same schedule, I believe, 9 to 5, 9 to 4, we get an hour off. But yeah, with that said, I will, I'll actually answer this question. Please, I'd like to know if RMG can simulate processes that were not involving oxidation or oxygen. It is now possible because sometimes back when we tested it, non-oxidative dehydrogenation of propane. Yeah. Does anyone know offhand?
I mean, if there's no oxygen in your,
If there's no oxygen present, the oxygen won't react. So if you don't put any oxygen in the input file, it shouldn't show up. But if it's in there for some other molecule, or like you've got water and it's being made, you could forbid it as a species and say, look, I don't want my oxygen, or make my oxygen inert or something, if you really want to force it to not exist. But otherwise, I would say if you're modeling a simulation of pyrolysis and you didn't put any oxygen in the reactor, then the oxygen won't react.